quick. Okay.
Yeah,
Welcome to
perfect time.
another exciting meeting of the Rutgers Zoom Experimental Math Seminar. Today we have Ido Kaminer, according to some person I want named, is engaged in intellectual fraud, but I strongly disagree. And he will talk about the Ramanujan machine. Go ahead to show your screen. As usual, please mute yourself unless you have something to say. Thank you.
Thank you. Let me share my screen and do a. It's actually the most unusual introduction I've ever gotten. You know, coming from areas of quantum and areas of physics, you can actually see my lab in the background. At the background, uh, going into experimental mathematics is quite an interesting experiment and a very different one. And I think that some of the culture in some of the mathematics community, maybe outside of experimental math, was somewhat more conservative when we started. But I think that by now it's quite established by many people that we have interesting stuff that we found. I want to show you like the most recent ones. Now I'll share the screen so we can go. But I'm also glad to hear questions on any type and discuss those topics. Can you see my screen? Is this working well?
Yep, looks good.
Awesome. Okay, so I think I'll start and say that we have started this project a couple of years ago, mostly as a matter of curiosity. It was a project that I was doing as a kind of hobby project with friends, some of them in different companies, in Google and others, some of them as undergrad students joining us at the Technion. And it spread with collaborators from different places around the world. And now also a bigger group at the Technion, with professional mathematicians also joining in. We call it the Ramanujan Machine project, and you'll see why in the next few slides. And I like to start talks on this by putting a few constants. And I think that with this audience, it's kind of obvious, and no really need to ask what those constants are. I hope everyone is with me. So that's just a trivial test. Do you recognize those constants? So of course, the first is pi, right? And the second is e. The third is also, I hope, trivial for everyone. That's the fun structure constant. What about the fourth? Anyone here recognizes the fourth constant?
Is that a 3 by any sense?
That is what? Say again?
Zeta 3? I'm not sure.
Yes, this is the
Zeta 3.
Yeah, or the a priori constant. And
Oh, yeah, Zeta 3. Yeah.
Yes, this is zeta of 3, or also called the a priori constant. And actually, it's nice to be in a seminar where people actually recognize this constant. So far, in different seminars I gave, the only audience that could recognize it were high school students, because they are in their phones all the time and they just check it quickly in Google. So they're fastest to recognize it. But here actually we have people that truly know it without looking it up. That's really wonderful. So I want to say certain things about experimental mathematics, and maybe I'll start with what I can call take-home messages. And that's, I think, this idea that when we think about how people do mathematics, how people make discoveries, right? It's been attributed to acts of creativity, innovation for many years. And in some sense, like when we think about experimental mathematics, it's trying to bring something new to the tool sets that we have in how we think about math, right? About like more creative approaches for how we do mathematical research. And this is the vision that's already there for many years now. And Doron is like one of the fathers of this field, right? But then what I want to show you today is how we built an experimental math project that has been expanding over the last few years, and is of course algorithm driven, but also massively parallel. So using distributed computing and having a large community of volunteers that is supporting it, in a sense that it allows us to make a major search with many interesting discoveries that it led to, especially over the last 2 years. And this led us to a discovery of an interesting mathematical structure that I want to also discuss here today. It's also pointing to interesting connections between mathematical constants that I think much of it is not yet known, with many more open questions than things proven, as you will see in the next slides. And I'll also present some of them, and really looking for like taking this opportunity to also suggest interesting open questions for people to think about. If I have time right at the end, I also want to talk about this idea of an archive or an OEIS of fundamental constants and their relations, and what type of connections will be useful to search in a structure like this, except for putting it in, also what type of searches we would like to have in a place like this. But maybe if I talk about experimental mathematics, and specifically the one that is looking into numerical constants, into the numerical representations, I think maybe some of you already know this example, but I think one of the most famous examples and earliest of doing this kind of search is by Gauss, who was having this really famous story of the 1799, when he was looking through tables of integrals at the days where you couldn't have them so easily calculated. So there were books by James Stirling with those. This is an example of an integral, and Gauss was able to make this really ingenious connection. Looking at the numerical value of this integral, he could spot its connection to the following. He was looking into the following recursion. If you take the regular average and this is the geometric average or harmonic average? No, geometric average. And then starting from those two numbers, 1 and square root of 2, right? Now calculate the two averages of that. So what will happen is that you will get like basically the next values of each one will get updated each time. And what you find is that if you start from the 1 and 1.414, actually going from right to left by mistake, this will gradually converge to a single number, right? Those two averages will converge to the same number. And this value, Gauss was able to identify it's being connected to this integral value. I don't know if you can see easily the connection between the two. Somehow Gauss managed to. I don't know how, but he saw that they are connected by the following relation. If you take 1 over, then they are actually connected by 2 over pi, or explicitly, the 1 over the limit of this averaging is 2 over pi times this integral. And now this is a famous case because it led him to, connecting averages to integrals, led him, and he is attributing this discovery of what led to later on the field of elliptic and modular function theory is actually attributed to this kind of connection that he made numerically. And I think this is a beautiful example, and there are more throughout history. But I think that with computers, we can have many, many more. And this is one of those examples where the numerical identification, what we call a conjecture, came much before a proof. This is what Gauss called, I have the results, but I do not yet know how to get it. So much of what I'll show you today is of this type. Our conjecture is awaiting a proof. And the type of structures we like looking into are those continued fractions. I'll say much more about them later on. And there are many continued fractions for interesting constants discovered over the years. This is one of the earliest ones by Euler, for example. And something peculiar and interesting about continued fractions, and I took here a couple of continued fractions of pi in particular, are the ones that we have here from Gauss, and this is actually from a paper from the 21st century. And this one is one discovered by the Ramanujan machine, by our algorithm. It's actually the first we discovered with the Ramanujan machine. And those are, in some sense, they're all very similar in style. They all have this shape that you'll have an an and a bn, two polynomials inside a continued fraction that will be, in this case, of a second degree and of a first degree. So it feels like there should be something connecting all of those. And I want to take a couple of slides to kind of give you a few examples of this, because what we really see more and more are families of formulas of this type. And it feels like it calls for this kind of idea of let's find a unified theory, something that will put them all together. And like those ones, we have more. This is a collection of continued fractions you can find in writings by Gauss on the left, and actually the ones on the right are by our algorithms. And those are all, they all feel very similar. And there are many, many more. By now, it became too easy. And I'll show you more and more of those. But it became too easy. We can find hundreds of them and can find much more. And that's like for pi, those are examples of continued fractions we have for E. This is and you can see that many of them are very, very similar. Like for example, the second line and the third line are almost the same with a slight shift between the two. So of course, it feels like there is some more general formula capturing all of them. And the last one here is slightly more complicated because those are polynomials of different degrees. But still, we would like to have a structure that will encompass them all, and maybe the last one here as well. And the same way we run those, there are many others, and it's again becoming almost too easy to collect them. And now it's true for E, it's true for pi, some more exotic constants, the Catalan constant. This is a constant for which whether it's irrational is still an open question. Catalan constant has this really beautiful formula that, to the best of my knowledge, was also first discovered by our algorithm. This is a relatively simple continued fraction. I think it's the simplest one that there is for Catalan. Though simplicity is something a little bit tricky to define. And there are many more, right? And we again see that it feels like those formulas are all of similar type. See, those AN polynomials are the ones here in the denominator, are all of this kind of shape with pretty similar polynomial. When we run this further, we find other types of formulas for the Catalan constant. And again, we have many more. So what I want to discuss today, and what really drives our research over the last, I think now more than a year, is trying to generalize this, trying to understand what's the underlying structure. And basically, I'll have broadly two sides for the talk. I'll have some part talking about the algorithm, or now the algorithms, because we have 4 that we developed so far that are looking into connections between constants and new formulas, especially for constants. And also, then the second part of the talk to try to find what's this structure that seems to capture everything, and we believe is a valuable thing to study also beyond the algorithms themselves. So that's the kind of general introduction. And now, if I want to talk about experimental mathematics, then as a whole, I think maybe adding a few more things to what I said at the beginning. I think this idea that discoveries in mathematics can be assisted by algorithms is now established. But then the most common scenario is where we have those algorithms helping us explore a large space of parameters that will be just too hard or it will take too long to explore manually. And then what I find really interesting looking forward is trying to find some way that kind of human intuition and algorithms will be able to connect in some interesting way. When people now talk about generative AI as the way that computers are now making the most impressive discoveries in AI, this is something that will be interesting to think where those types of algorithms could be of value to what we do here. And what I can show you today is no LLM in the game, but still something that is generative in the sense that it provides formulas also of structures and shapes that we did not expect. And what we have behind the scenes is a massively parallel algorithm that by now discovered an unprecedented number of formulas. And I think the largest number of formulas for constants that is known, and that is something that we placed on archive about a month ago. And it also led us to some discoveries. And this is what we call the conservative matrix field. And the conservative matrix field is the structure I'll devote the second half of the talk to describe in more details, because we believe that this is the most elegant way to unify those thousands of existing formulas for each constant. And it, of course, enables generating infinitely many more. It's also leading to interesting relations between the different mathematical constants. And it might be a powerful method to help prove irrationality for some of them. We, for example, reproduced the a priori proof of irrationality of Z of 3 and we managed to generalize it to other constants, although not to super famous ones. Otherwise, I would be declaring this at the beginning. But we're trying to find other ways to generalize this, for example, to Z of 5, and I can say a few things about this at the end. So let's go a little bit into the algorithms. What we have done first when we started looking at this problem is thinking about the original, seeing so many formulas for pi and other constants of very similar shapes, is we thought we want to have some kind of black box enumerator This will be getting a bunch of parameters into it. Like in this case, if we have a continued fraction with a an and bn as two sequences, we can imagine two polynomial integer sequences. And then in the case that we have here, for example, we'll have 6 parameters to enumerate over. That will be integers, negative or positive. And then we'll want to make this, the output of this, match to a certain constant, for example, to pi. But actually, it's not necessarily having to be pi. It could be 1/pi, would be as interesting, or maybe a pi square, maybe a square root of pi, or some other, we like having rational functions of pi. And those kinds of combinations mean that in some sense we have 2 sides for the equation that we want to enumerate over. On the one side are the parameters of the continued fraction itself, and then on the other side we have the manipulation on the constant that we like to search. This is the first thing that we have done, and a very powerful method for this is well known for many years. It's called meet in the middle. Meet in the middle is an algorithm using hash tables. So the basic idea is that you enumerate a bunch of continued fractions, you save their numerical values into some hash table, you save a certain depth, because you know that this will basically, both in terms of memory, but also in how long it takes to calculate to a certain depth. And then you're looking for, and then you save this table. It takes memory, but it saves us in time. We then enumerate the other side. We enumerate over combinations on those constants, for example, rational functions on those constants. And then we look for those constants, the resulting modified constants in the same table. Whenever we find a hit, we call it a suspected formula, but then we enumerate further digits, so we have sufficient precision to call it a real result. That is something that will be interesting to try to prove. And this type of approach led to many beautiful formulas like this one. And the majority of results we had at the original paper that we published now 2.5 years ago, this was the paper in Nature in 2021, were coming from this algorithm. The second algorithm, and there are multiple other tricks that improved it, like a Bloom filter to be used there, and you can read more about this in the paper. But this, by the way, was originally suggested by Uri Mendelovich, who was a colleague and a volunteer in the project worked at the time at Google, and he's still working with us on different ideas. Then the second algorithm we had at the time, and this is the one I mentioned, despite it not being the most successful, but it is the one thing that everyone is asking me about, because it is the closest to something that you can call a neural network in a sense. It is an optimization algorithm where we are using gradient descent to look into a formula, for example, of this type, this shape, right? You can take the polynomials and now treat the same parameters that we had before, but now treat them as continuous variables that we want to then calculate the gradient descent over. And let's say we look for a formula that will converge to like pi or e. What we can do is put a bunch of variables here. In this case, I only took 2, x and y. And then you can force this to be equal pi, ask what's the error, and calculate derivatives on the error. Derivatives as a function of x and y. What's beautiful about it is that you have to do a recursive derivative, and because x and y appears infinitely many times inside. And this recursive derivative will mean that we have a calculation of a type that is actually very common in recurrent neural networks these days. So you can actually use the same tool sets and methods that are used to calculate those things to make things faster. This is something that Yael Manor developed, and her approach was really beautiful, because we had to do much more. We found too many results that were not interesting, and then we had to find the interesting ones between them. So we had a gradient descent that we called a descent and repel algorithm, where we forced different initial conditions to repel one another and try to search for integer solutions in particular, because it's too easy to find solutions that are not interesting, like arbitrary values that we cannot attribute integer number to them. And that's basically what was the second algorithm that we developed at the time. Now I want to make a big jump forward, because over the last the 2 years, and now more than 2 years since then, we had new people joining the group, and I think way more powerful algorithms that are not as famous now, but because we just placed them on arXiv a month ago, and I want to go into those ones. But for them, we'll need to go a bit further into the mathematics of continued fractions. I don't think I need to do any introduction to actual continued fractions. I'll just say briefly that when we calculate the simple continued fraction, which means that all the numerators are 1, we'll have every rational number have a finite sequence here, while irrational numbers will have an infinite sequence. And then in many cases, the simple continuous fraction, which is, there is only one way to write it for every constant, it will not have a simple sequence. Like for pi, we'll have this very regular sequence where no one knows whether there is a simple formula for it. But those are the simple continuous fractions. The ones we are after, and you saw in the previous slides as well, are more general ones. When we generally think about simple continuous fractions as one with numerators of 1, generally you could have any sequence of numerators and denominators, but we specifically like the ones that are, we call them PCFs, or polynomial continuous fractions, where both the numerators and the denominators are polynomials, where we originally worked with integer ones, now we more often work with rational ones. And generally, structures of this type are, I think, very powerful and interesting for study. And partially, this is because they are, on one side, computationally very convenient to enumerate over, and on the other side, they have a very broad mathematical scope. They capture many structures. You can write Bessel functions with them. You can take any infinite sum and many hypergeometric functions and convert them to polynomial continuous fractions. So they are pretty convenient on both sides and pretty general and still convenient to work with. And now one of the things that made them famous is the usefulness of the polynomial continuous fraction for their Apéry constant. Apéry's constant, right? This is the zeta function of 3. Is also famous in physics, appearing in many areas of statistical mechanics, and it got the name Apéry's constant because Apéry was the mathematician that managed to prove its irrationality, which was an interesting question. And what he did in order to achieve that, he actually developed a continued fraction, a polynomial continued fraction, which by now I think about this as a beautiful one. I don't know if you all have the same taste, but this specific polynomial continued fraction is a very important one because it is converging quickly enough to prove the irrationality of zeta of 3. So I want to say something about irrationality and in this context, and also keep the question in mind that what many people thought about for many years now, and we are also thinking about, is whether we can generalize his approach to other constants. And I think this is something that we may be able to do with the type of structures we are now seeing, and I hope we'll have much more to say about this. So how do we connect between a polynomial continued fraction and a proof for irrationality? What we have behind the scene when coming to calculate a polynomial continued fraction is that we can always truncate it at a finite depth, and those are the convergence. We'll call them Pn and Qn, and you can directly calculate the Pn and Qn's, the numerators and denominators, with a recursion that will look like this. So the same An and Bn, those are the numerators and denominators, will appear as the coefficients of this recursion. And the coefficients for the case of Apéry were those ones. And that allows you to calculate separately numerators and denominators, and then get a sequence of rational numbers that will converge to the limit of the continued fraction. And then a sequence of rational numbers is exactly what we need for maybe the most famous way to prove irrationality of a number, right? And that's the Roth theory, that is, the irrationality measure of a number will be can be evaluated in the following way. We need to find a rational sequence that will converge to that number, in this case L, and then we'll look for a delta. Delta will be this irrationality measure that will allow us to bound this limit. So we need to find, in a sense, a sequence of numbers as small as possible. So Qn will be as small as possible, the denominator, and still converge quite quickly. And that's the kind of intuition behind it. And then typically we know that for deltas at 0, the number is rational. For 1, it's from algebraic irrational to more complex, like transcendental. But then it means in practice that whenever we find a delta that is larger than 0, we know that the number cannot be rational. And there should be another sequence that will also be giving us a delta of 1. But that's why it's sufficient to find a single sequence of a delta of larger than 0 to prove the irrationality of a number. And that's exactly what Apéry did, where this specific sequence gave a delta of 0.08, and that is larger than 0, and therefore proved the irrationality of what we now call the Apéry constant. Now, that's an interesting question to ask. Well, what's so special about those two polynomials? Which pairs of polynomials will be valuable to prove irrationality of different numbers, with different constants. And that's what the kind of things that we want to find. And we spotted an interesting property that I want to highlight that appeared in the Apéry's formula, but it appears in actually every formula we tested for other constants in the history of constant of formulas for pi and e and others, and actually in everything we discovered with our algorithms as well, even though we did not look for it. So I want to talk about this property because I think it's a quite interesting one. We think about it as a kind of a miracle in numbers, and this is what we call factorial reduction. If we think about, for example, the following formula, this same property is also true for Apéry's, but I took a simpler one. This is the formula for pi, and you look at the partial convergence, so those are numerators and denominators. You'll find those they grow quite quickly. That's not super surprising because this is a recursion with polynomial coefficients. So numerators and denominators typically grow like a power of a factorial. But you can then ask, what will be the common divisor? What's the GCD? And the GCD, interestingly, also grows very quickly. Now, this is not a trivial thing. If you take any other formula, let's say this one, so it's also squares here, but this is a different linear formula as the denominators, and you try the same thing, you also find that the numerators and the denominators grow quite quickly, factorially, but the GCD will actually grow much more slowly. And if you try now randomly many pairs of polynomials, you'll find that the most common thing is to have the GCD not growing factorially. But for every formula we found for Catalan and pi and Z of 3, and we found many for Z of 3 by now, we always had this factorial reduction property happening. So there is some kind of conspiracy, you can say, that formulas that go for constants tend to have this property. And that is, I think, a pretty interesting thing. You actually find it also for infinite sums that converge to constants. It's not only for for PCFs, but for infinite sums, it's not so complex to prove. So I'm not sure whether this is on its own a surprising fact or not. For PCFs, we do not know how to prove that, or not how to predict it either. And you can read more about this in our paper from 2 years ago, or soon to be 2 years ago. It was end of 2021, and now we're writing a revised version of it that I hope will be online very soon. So if I for a moment quantify what we now talked about, so what we are looking for is a case where the reduced numerator or denominator, both the same way, so Pn over the GCD, will no longer, it's not just that the GCD is itself factorial, it's even doing more. It's dividing all the factorial part of the numerator. So Pn over GCD, the reduced numerator, will itself grow just exponentially, which is kind of the slowest you can imagine something going in a case like this. So the nth root of this will actually go to a constant. And those are the cases that we're looking for, because they tend to be very common for formulas, even though they're rare in the general sense. We call this number, this is the base of the exponential, we call it S. And we'll talk more about this. Now, so if I summarize this part with a few notes, this is the work by Nadav and by Guy. They were undergraduate students working with me at the time. We think about it as a miracle of factorial reduction. It's extremely rare in random polynomial continuous fractions. It still appears in all historical PCF examples that we ever tested, and also in all the ones that we find numerically, and now we have many. And it's really an open question then still today, what continuous fractions will have factorial reduction, and how to identify them in advance. Now, why is this so valuable to us? Because once we know that there is factorial reduction, we can also predict what delta will be. If we know this S, then it's not hard to find the roots of this polynomial. This is having a and b are exactly the leading coefficients of the an and bn. You can calculate those two roots. The ratio here, ln of s, that's the base, and then predict delta. So that's a pretty convenient way to think about things, and this works perfectly for Apéry's result and for many others. Sometimes the delta is positive and sometimes negative. It will not necessarily prove rationality, but it's still pretty useful. So if I now go for our next part of the talk, we saw this miracle, and it completely changed the strategy for our development of algorithms, because we now have this property, and we said, why not use that to look for formulas relying on this property? So now this is a very risky move because it's a conjecture that seems to occur a lot in nature, but we started looking for results based on this conjecture. So that what's happening is that our most recent algorithm, and the most successful by far, is basically saying, let's look for continuous fractions that satisfy this property. We do not know what constant they actually converge to, or whether at all, but we still look for those constants, for those formulas. And that's our strategy. And the general idea now is that this is a very convenient strategy because we only need to worry about one side of the equation. We don't care what constant we need to converge to. So it makes it possible to develop much more creative algorithms. We have this database of that we build at home, and this is what we use to define strategies for enumeration. We then inserted a search scheme for the network search algorithm. BOINC is the Berkeley platform for enumerating over computers by volunteers. We send many areas of continuous fractions to search for, and whenever they find factorial reduction, they send them back, and then we verify them and we update our database. This is the work that was led by Rotem Elimelech, who has now finished his undergrad after working on this for a few years, and is the lead author on our most recent paper. And this is also a very powerful strategy that led to a lot of results. It also got us very involved with the community. You have users that are starving for more jobs, hungry for tasks, and many funny interactions like this. But this will be for another talk. If you're curious to see how it is interacting with the wider community, it's quite a fun thing. But now, something about results. So once we do not have to know in advance what's the left-hand side, this made it possible for us to make discoveries of formulas that are just insane to think about. I took 3. We have hundreds. But this is, look at the first one, for example. I think it's just beautiful. We call it a zigzag zeta formula. There is a zeta 5 minus zeta 4 plus zeta 3 minus zeta 2. And you can actually guess how this generalizes, and it's not hard to generalize. We have zigzag zetas for any order of zetas that you would like to have, and many more general structures of this type. We also have crazy ones like this. This is something combining zeta of 3 and pi to the 3 together, or this one that combines zeta of 5 and zeta of 3 with more complex coefficients. And we have things that combine zeta of 7 and zeta of 3, and many fancy formulas that we can find. There are also infinite families. Those are all formulas for combinations on zeta of 3, that once we found a couple, we could generalize relatively easily and say what's the general case.
Conjectures officially, or they're proved?
Conjectures. I believe that we can prove the ones on the right and the one at the top, and we have some scheme for this. The ones at the bottom, not really.
Okay.
And
start for the left-hand side, and then you get the right-hand side, or you start from the right-hand side and try to get a nice left-hand side?
You mean what way we actually prove them?
Or derive them. So you just start with.
So the way we find them is that we enumerate over the polynomial continuous fractions, and then we find a polynomial continuous fraction that has this factorial reduction property. We say, okay, this is a suspected interesting one. It should have an interesting constant connected to it, and then we say, okay, this looks like order 10 here and order 5 here, so it's probably related to zeta of 5, and maybe a few lower order zetas. It was actually a guess that Rotem made and was really beneficial. And then we use PSLQ, that is worth itself the entire talk, to look for connections given the couple of constants that we know for. It's kind of high order connection using PSLQ, and in this case, PSLQ is the savior.
Okay, that's beautiful.
Yeah, so that's the strategy now, and that's why we can find those crazy things, because basically it's the factorial reduction plus PSLQ is making it possible to find many more. And now, what will be where I want to take us for the final slides of the talk is to say, well, once we have so many, and I started and alluded to some structure, let's talk about what generalizes this whole thing, because I think it is quite interesting. And I will take this table on the right to continue with. So the next step is to try to build some mathematical structure that will generalize what we saw. And for this, I'll also remind you that we had a bunch of related constants for pi, and we had many more. So let's go back to this table. What we have here, basically, right? Each line in this table is a formula for zeta of 3 or some modification on Z03. And it means we have a sequence of rational numbers that converge eventually to Z03. But then what we wanted to have is, then could there be also a similar step? Like what's the step to the right is basically another level on the continued fraction calculation. But could there be something like that for when we go further down? So there should be a transformation between rationals going downwards instead. And that's something we can do. I think what's behind the scene and very convenient to use is that there are a set of matrices that we can apply on those pairs of rationals that will take us, pairs of integers that form a rational, that we can take us either to the right, this will be what we call mx, or take us down, this is what we call my. So basically there is a way to construct motion in both directions. And then it's natural to look for matrices, because if you think about the continued fraction calculation, you could write it as a recursion like this, but you could also write any recursion like this in the following sense. Right, you can write the numerators and the denominators in a matrix, and then basically multiply many matrices of those polynomials. And in this case, this will be the Apéry matrix. And actually, every matrix like this can also be transformed. There are simple tricks to convert some of the polynomials, and we can flatten it in this way. And numerically, this is way better. So that is the Apéry matrix as well. So what we are building is the following kind of thing. Now, actually, I take the y-axis upward. So we are actually looking for a structure where if we start at the origins and we go right, it will be like walking along the continued fraction. And if we go up, it will be going to the next continued fraction in this structure. And what we need then are matrices with this really interesting property, because if we go right and then up, or up and then right, we should get the same thing. And that property is what the formula you can see that you have here on the right. Right? We call this a conservative matrix field, in the same sense that you may know a conservative vector field. Right? In physics, this is super common. We calculate an integral along a vector field. We want to get the same value at no matter what trajectory we took. Right? This is the conservative vector field. So in some sense, the conservative matrix field is the same creature, but in integer steps and relying on a multiplication of matrices. And so conservative matrix fields are, when we find more and more examples all the time, are powerful tools to exactly find the formula. So for example, if we take the following matrices, the ones we have here, you see at the top, this pair of matrices will be exactly the ones that will give us many of the E formulas, or maybe all the E formulas. We do not know how to prove it, but we managed to derive many E formulas, both ones that have this linear shape and also ones that have higher order polynomials in their structure. So it seems like a structure that will be pretty useful, because you don't have to walk along horizontal lines. You can start walking along vertical lines instead, or even diagonal lines. And each trajectory you take will be a new formula for E. And that is one of the interesting properties we find here, is that no matter what trajectory we take, along certain ranges of angles at least, we get the same limits. And that's one property that is very important to prove, and we have only very partial proofs for it. Because it seems that if you start at the same point, you walk along different trajectories, you get the same thing. And that's a pretty nice thing, nice property that also helps us find many formulas for the same constant. So E has its conservative matrix field, and it's let me, for those that are still confused about the definition here, take a moment. We actually use the if you know 3 blue 1 brown is really a genius in communicating mathematics, and also made this beautiful Python package for communicating mathematics. So some of our students, Eyal and Michael, made a small movie. And so I took a small part of it just to show that dynamically how the matrix multiplication is happening. So this will take us a minute. But if we start with the origin and now multiply by different matrices, what we get, those matrices are derived by the formula I showed you. We basically see that we get the same results no matter what trajectory we take. And now we can do the same thing with much more complex trajectories, remembering that the matrix is evaluated at the coordinates, right? So we basically multiply those matrices in succession, right? And this is a procedure we do numerically. By now, that's very quick. And if we try and basically follow those matrices in different directions, those matrices basically preserve this conservative property wherever you go. And then the next step will be to zoom out even further. And now imagine you take a trajectory that takes you all the way to infinity. That will be the powerful method that will really bring us to to different formulas in different directions. And now it's interesting that it's not so simple to it's not so simple to find formulas like this. If you change a single value in the matrix, it will not be conservative anymore. So it is a pretty rare property for formulas to do that. Also, interesting to note, the conservative matrix fields do not have to be two-dimensional. We by now got three-dimensional and five-dimensional one. The one for the Catalan constant is 5 or 6-dimensional. It's a debate in the group right now. So those could be, and we do not know how many dimensions will be in total for each constant, but it seems that there is some rule for that as well. Also, there do not have to have a direction that is exactly a polynomial continued fraction. This creature itself is more general. So we have matrix fields where no direction is explicitly a continued fraction, and it does not really matter so much. So we can actually do that same thing, but just forgetting about continued fractions completely. And this allowed us to find similar continued matrix fields. So this will be a pair of matrices that we'll call the matrix fields for pi. We believe that there is a third dimension. We do not know how to prove that all of those are inside yet, but we did manage to develop many of them with those pairs of matrices. So I believe we could probably find them all. If we go back to Z03, this is the work by Ophir David from our team. So we have this pair that I think is pretty elegant. And here is something really nice about the matrix field. You can derive a formula going right or derive a formula going up. And those will typically be converging quite quickly, quite slowly. And the rate of conversion matters if you want to calculate many digits or if you want to prove irrationality. So what we found here is that if we go in diagonal, we find a much faster convergence. And actually the diagonal of this matrix field in particular is quick enough to prove the irrationality of Z of 3. And that's something you can read in Ophir's paper that's on archive for a few months now. And not just prove the irrationality of Z of 3, but it actually reconstruct the exact same polynomial continued fraction by a peri. And that's a pretty nice thing. So there is a Paris result in some sense is equivalent to this diagonal. Now, what we tried is to do the same for other structures, to look for diagonals of other continued fractions. And it seems to work in some cases. For Z of 2, for example, it's quite easy. Also for the third root of 4 and a bunch of other weird roots and a bunch of other constants, but so far not for something very surprising. And it will be wonderful to find a conservative matrix field for Z of 5, for example. We did use this method with Catalan, and we do have the world record for the fastest convergence for the best irrationality measure for Catalan, but not a positive one yet. So this seems to be a powerful method. There is also a generalization of the formula that we had before for predicting what delta will be, but now we don't take the roots of the polynomial, but instead we take the eigenvalues of the matrix. There is also a similar property that we call factorial reduction for the pair, but it works for the entire matrix. So it's the GCD of the 4 elements now. And this is opening a question that there seems to be a connection between the matrix, the property of factorial reduction to at least some of the matrix fields. And that's an interesting game that we do not completely understand. So if I take the last few minutes to start summarizing, I want to advertise a couple of questions and things we're seeing here. Because we had a bunch of numerical experience by now. So for example, an interesting observation is that there are matrix fields that are kind of cousins to one another. So for example, if you take pi square and Catalan, they will have exactly the same matrix field, but shifted. So imagine you start with a matrix field that moved the origin by 1/2. It means that the numbers you substitute into the matrix are shifted by 1/2. You can do it in one axis or in both, or along other dimensions as well. What will happen then is that we still preserve the same properties. You can show quite easily that the properties of factorial reduction, for example, will be preserved, but you will not go to the same constants anymore. So there are connections between different constants by the same that all reside in the same matrix field up to a rational shift. And in that sense, we try to start collecting, can say clustering different constants. Because if pi square and g sit together, and it seems like a peri and pi to the 3 sit together, you can kind of build a hierarchy. There will be the simplest matrix fields for pi and square root of 2 and other things. There will be the more complex ones for pi square and g. There will be basically families of matrix fields, and that's seems like we can really organize them in complexity by the orders of the polynomials that construct them. There is some connection to factorial reduction that we do not completely understand. There are also this beautiful property of convergence to the same constant along different trajectories. We are finding cases where this is breaking, and conditions like there are certain angles where this is breaking. For example, the Gompertz constant and E reside on the same matrix field, but at different directions. And there is what seems to be singular lines that basically make sections in space between them. And that's an interesting area to look into as well. We basically have now we have a team of people that joined us with different backgrounds, some more computer science and some more mathematics. And we're looking into a bunch of questions that are opening up here. And I think I'll not go through other open questions, although I'm happy to discuss them later, because I want to take 2 minutes to talk about this library that I mentioned at the beginning. Then this is the kind of what we think about, it's the archive or the OEIS of fundamental constants. What you know that there are many more constants that are interesting to think about. I like the Feigenbaum constants. If you're not familiar with them, look them up. They're connected to chaos theory and to fractals. There are many more constants. This is a book of mathematical constants from exactly 20 years ago. And what we did is collect everything that we can find online to a single database, but also put in it a large collection of formulas, basically everything we find that is an integer sequence-like formula. So there will be a recursion-like formula, or an infinite sum, or a polynomial continued function. We have cases where we found factorial reduction for, so we believe they are connected to some constant, but we did not find what constants they are connected to. And the majority, we managed to find a constant to connect them to, or a combination of constants, like what I showed you before. So that made us think that there should probably be more complex connection. We just didn't realize what they are yet. So we are basically collecting a large collection of formulas, and then the strategy is to use this kind of database to find smart search tools like PSLQ, something that will find integer relations between the constants, to try to find new relations between them. And this is something we're working on now, and I hope we'll put online soon and show that it's valuable. This is actually a good test. We never know before we run it, and we'll see this soon. So this is basically the kind of game we are having now. We are running this on AWS, and we're planning to put an interface, Python interface for everyone to use. And we're happy to hear more ideas there. The basic search we are having as a step one is this kind of thing. We have the constants as x's, and the a's will be integers, and we want to find relations of this type. I think this can discover quite a lot of things. I can explain more and why exactly. And this will be something accessible and I hope useful. And I will be glad to discuss more and hear ideas on this. But I think I'll stop at this point. There is much more to tell, and I'm glad to discuss with you guys. And I'm happy for the invitation. Thank you, Doran, for the chance and for the interaction.
Thank you, Ido. This is really very, very promising. It's really the future. And to be a continuous analog, I guess, of the OIS and all these relations. We have time for questions. Any questions for Ido?
Yeah, Ido, I had a question. You have this, I don't know how you pronounce the acronym. I'll call it BOINC. You have this big BOINC search that you're doing. Are you also recording the deltas that you're getting from this when you're doing these distributed searches and getting the results back?
So actually, since we're looking for factorial reduction in particular, so we do not know whether there is an interesting delta. And actually, we just tested it a few months ago, and the majority of results we're getting have a boring delta, a delta of -1, which is kind of the most technical one. So it means this is not a guarantee for an interesting delta. We're now thinking about, and we started working on an algorithm that will be saying basically, let's search for things by the delta. Instead of looking for factorial reduction, which we like and it's promising, let's look for the delta, just directly the delta. Can we search for, we just started very rough searches and we got too many results. So it seems like there may be entire regimes of polynomial continuous fractions with trivial deltas. I don't know. So we will see soon. I'm happy we can discuss this more. It's and I'm glad that you're here because we were chatting on this when we were just starting. Yeah. Other questions for
in the chat by Conrad. Can you look?
Research for
Structure constant.
Oh wow, this is a super interesting question for us. So the fine structure constant is a physics constant, but it is also dimensionless. So you can say that is not dependent on what units we use. It's really an intrinsic constant of nature. And actually finding a formula for that would be amazingly important because fine structure in particular is connecting the charge of the electron, h bar from quantum, and c, the speed of light, the same formula. So that will be amazing. The problem is that we know about something like 12 digits of the fine structure constant. And that means that if we start running algorithms after something like 10 to the 12 space on that scale, which is not so big for computers anymore, we will start finding results. And they're random results. So it is too easy to find formulas for the fine structure constant today. And that is now a question of what is, if it's a really beautiful formula, maybe a simple one, you will say, oh, this is surprising enough. So we are getting into a regime that we need to define what's beautiful enough to be considered legit in a space of, or push experimentalists in physics to get more digits, but that's very hard.
If you go back about 20 or 30 years ago, someone did exactly what you're doing with the fundamental physics constants, published a paper showing that a whole bunch of them were related exactly the way you've done it. And then someone else showed statistically that had to happen and that his results were meaningless. I'm sorry, I don't know the paper, but it was about 30 years ago.
Years ago. If you find it, please send it to me. We actually had an attempt to build an algorithm like this with a friend who's part of the team, and we ran an algorithm of this type. We were analyzing the error very carefully, and I got a similar result to what you're describing, but we took many more constants from physics, and I think one of the reasons we found really nice formulas there is that we took not just the fine structure, but you can derive a whole bunch of dimensionless constants in physics. So we had a large space of things to search over. We did not publish it yet because we wanted to be very careful about the error analysis. And I believe
you better find this paper because
yes,
statistically it was shown that this had to happen.
Yeah. So, so there are papers after it that show that it was not.
Yeah. After he had published this, I'm sorry, I read the original paper quite a long time ago, and then sometime after, somebody else published it, showing that it had to happen. Statistically, he had to discover relations.
So it's a little bit like
the size of the search, right? It depends on the size of the search. And so what happened to us is both papers together. We started and we ended up saying, well, nothing there is conclusive. That's it.
Yeah.
Anyway, it's all I can add.
Physics is speculative, but the mathematics is very solid. That's really very, very exciting, all the relations.
Yeah, in the mathematical constants, just for context, in the mathematical constants, we can always get more digits. We only work with ones we have many digits for. So it's much more solid. But yeah, that's a big difference.
It's really exciting. It's also very impressive, all these undergrads, the army of undergrads that you are doing very, very meaningful in your research, how you motivate it. That's also sociologically, I think, very.
You know how this started? This started with undergrads, partially because I thought it is too risky to take graduate students to work on this. And I did not want to sacrifice anyone's career on not knowing whether it will work. But it worked so well, and now it's expanding to a point where we have the first graduate students also working with us. And we're looking for more students that will be interested in working in this direction. And we had a student publishing one algorithm I didn't mention that we published in ICML, this machine learning conference. I think that we are now in this borderline of between machine learning conferences and experimental math conferences.
Yeah, this is interdisciplinary, and this is a little bit dangerous because whenever you have innovative research between cross-cultural one, because people
it's also risky which community will, but I think this is becoming now more broadly accepted, partially because AI for science is becoming a very hot topic. So people see the first things we have done in this as a part of the birth of this field, and that is there is a thing. So they're more accepting to this kind of idea, at least in the machine learning community. I don't know yet about it. There's a question, integrals. Do you have algorithms to find integral representations for mathematical constants, like the one you showed in the beginning? So no, I'm happy to discuss on this. We did not try this at all so far. I know that there are important integral structures for constants like zeta and combinations of zetas as well in works by like Zudilin, for example, right, and others. And those are may be related. There may be a connection between them to the conservative matrix fields, and that is something we're about. So I'll be happy to discuss this further. On connecting integrals to recursive formulas. So I find that like this would be a clue to connect the things, but I don't know how to make the connection yet.
Yeah, it'll be very interesting. And when we let you go to sleep, it's 1 a.m. the next day for Ido. Thanks so much for a great talk. It was so fascinating. And the recording will be available next week. And you feel free to email me the slides so I can post them as soon as possible. Thanks so much and good night. Laila Tov. Thanks everybody for and see you in 2. Bye-bye.
Thanks, everyone.
Thank you.